And let's just observe a very small example. This is called, I should have put this here. We call this guy PGNQ. That explains why I started with the n plus 1, because I want to reserve the n for this notation. PGNQ, the n-dimensional projective space over the field with q elements. So let's look at the one-dimensional space over the field with q elements, the smallest guy. The vector space, fq squared, the n plus 1. What are the one-dimensional subspaces? Well, I could form, let's say, like this. The vector 1, 0, certainly a subspace. And then I have to also consider t, 1, where t is in fq. Okay? Think about it. This covers all the one-dimensional subspaces. Every one is listed once in this list. Let's do a quick count. We have q possibilities here and one more, so we have q plus 1 points. The line is just the vector space itself. It's just one line. This is the projective line over the field with q elements. Think of it like this. And label these dots with these points in any way you wish. So that doesn't look too exciting. So maybe it's time to move up to the second dimension. Is that clear? Any questions so far? So let's move up to dimension 2. In other words, projective planes. The vector space is fq cubed. And the set of points. And check that I don't forget anything. So I could choose something like this, x, y, 1, where x and y are in fq. Yeah. That's already q square possibilities. That's not all, because I have the 1 in the rightmost coordinate. So I'm forgetting about the subspaces where there's a 0 in the rightmost coordinate. Well, but that's the case from before. That's the case where I have 2 homogeneous coordinates. That's the projective line, and we've done that already. So let's call it c, 1, where c is in fq. Union 1, 0, 0. So let's do the count. We get q squared over here, and we get q over here. So you get, q plus 1 over here. So total number of points, q squared plus q plus 1. And draw a little picture. You just start out with the xy plane, coordinate plane. And you can think of this point x, y, 1 as just sitting here at x, y. So this would be the point x, y, 1. And this is a q by q grid. Okay? So they're jumps from one point to the next. There's nothing in between. Okay? It's a discrete object. This, nevertheless, is still called the affine plane. So the same object we're familiar with over the, let's say, real numbers. Now we have to talk about these guys. These guys are called the line at infinity. And so let me first finish this off. L is the set of hyperplanes. So two-dimensional subspaces, because we're in 3 dimension. And you can show that the size of L is also q squared plus q plus 1. Same number of points and lines. And so where do we draw this line at infinity? Just draw it somewhere, but don't mix it up with the affine points. So for instance, we have this point 1, 0, 0. And then we have all the points of the form c, comma 1, comma 0, somewhere over here. Okay? The line at infinity, and how does this make sense? I'll have to now tell you about how we go from the affine coordinates to the projective coordinates. So this would be an affine point. We have affine coordinates x, comma y. Now you want to know what is the relation between the affine coordinates and the homogeneous coordinates. So here you would have a point x, comma y. I'm using lowercase letters. And here you would have a coordinate triple x, y, z. And the relation is you substitute little x is capital X on z, and little y is capital Y on z. If you do this relation, you can go back and forth between the affine plane and the projective plane. Have you seen that? Yeah, you've seen that. So let's just keep this simple. So this would be called homogenizing an equation, and the other way around is dehomogenization. Let's just do one simple example, okay? So let's say if I have a line, y is mx plus b, then I would homogenize. So let's draw the picture. So let's say like this. This would be m over 1. This would be b. Homogenize. Homogeneous just means that you have a polynomial where the terms all have the same degree. So you see here you have degree 1 and degree 0 terms. So that we would say this is not a homogeneous polynomial. So what you do is if you substitute y on z for y and x on z for x, then assuming that z is non-zero, you would have that y is mx plus bz. And now the magic comes in. Now you put z equal to 0. Okay? Put z equal to 0, even though you just said in the beginning, let z not be 0. Gesundheit. So if you put z equal to 0, what you would get that y is mx. And in other words, you would find a solution. Well, let's first find the solutions here. You would find the point x, and then y is mx plus b. If z was 1, then y is mx plus b. And this was little y. So you recovered all of this in this homogeneous world. But now let's put z equal to 0, and we will find, let's say we put x equal to 1, we would find that y is equal to m. We found another point that lies on the projective version of this curve. So the picture is now you would draw the line at infinity, and you would see that this is, by the way, the same as 1 on m, 1, 0. And so you would figure out that this is the point 1 on m, 1, 0. Up there. You've gained one more point. And this is often often helpful to gain these points at infinity. Theorems become more clear if you move the theorem into the projective world. You can prove nicer theorems. Shall we do one more example or just move on? I have one more example here, a conic. So let's start with this one. Famous circle equation in calculus studied. Now let's just consider it mod 5. Use 5 was our example. Let's just do the same thing over f5. And now let's see how this really looks like. 1, 2, 3, 4. 0, 1, 2. So think about it. I claim that you have this point here because x is 1, 1 squared is 1, and y is 0. Solves the equation. You have a point over here, and then symmetrically you have a point here and here. You find these 4 points. Now the question is, what would you get at infinity? So at infinity, well, we have to do the substitution. X squared and z squared plus y squared and z squared equals 1, which gives us x squared plus y squared equals z squared. And we put z equal to 0. And we find x squared plus y squared equal to 0. How can we solve x squared plus y squared equal to 0? Well, we're going to do a little table over here, x squared mod 5. So plug in 0, you get 0. 1, you get 1. 2, you get 4. 3, you get 9. Mod 5 is also 4. 4 could also be called minus 1 if you want. Mod 5. So observe that you could put something like 2, 1. 2, 1 or 3, 1, for instance. You could also put 1, 2. You could put 3, 1. All of a sudden we have 4 points. We've got 4 points. Now wait a moment. We have the issue that we have duplicates. So which one goes away here? Wait a moment. What do I have? 1, 3. Multiply this by 3, you get 6 mod 5 is 1. So you get this guy. These are the same point. And multiply this guy by 2, you get this guy. Okay, so in reality, we just have 2 points. Okay, so let's say we throw away these. And then this would be, the line at infinity would consist of the points 2, 1 and 3, 1. Okay?